This video is produced as a study guide for students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. This video is the second of a two-part series. The discussion will be on diesel engine emission reduction. Our first subject is exhaust gas scrubbers. Today, there is an environmentally controlled area 200 miles off the North American coast. That is, those ships that are entering an environmentally controlled area, they're coming in within 200 miles of land, must lower their NOx, their SOx, and also particulate levels. Now, for the SOx reduction, if you are not burning a low sulfur fuel and one that's a clean distillate, you can continue to run heavy fuel oil if you switch over to this exhaust gas scrubber. And the exhaust gas scrubber removes the SOx and the particulates from the exhaust plume by spraying water into this scrubber, and literally almost like a shower, that water is atomized. You will have trays within the exhaust gas scrubber, and those trays typically will have either rock or it almost looks like a ping pong ball, and the exhaust gas is coming up through that media, and you're spraying, I guess if you want to call it sprinklers, spray the salt water onto that to cool it and to saturate it so that the sulfur will be carried away with the salt water and also the particulates. So exhaust gas scrubbers can be configured as either open loop, closed loop, or hybrid. In open loop, you're using it again this salt water, and salt water has a natural alkalinity, and that is used as a buffer on a once-through basis to neutralize the sulfuric acid. In other words, you are spraying that salt water to clean out the SOx, and then once it drains down to the bottom of the scrubber unit, you're going to discharge that straight into the ocean. Typically, though, that wastewater is treated and monitored before being discharged into the sea, and you will remove the particulates. But it will affect, in an open loop system, it will lower the pH of the salt water entering the water. One of the things on this issue is pH of the ocean is becoming an environmental concern. But those regulatory agencies that are looking at this feel that the rising CO2 level in the world's atmosphere will have a much greater effect on the pH of the ocean through the creation of carbonic acid than this discharge of sulfuric acid from vessels. So this will be something that will be looked at and argued over the next few years. Then closed loop. And the closed loop is best suited for full-time operation in low alkalinity areas such as the Great Lakes inland waters. So when you are in a freshwater, and this may even include, we'll see how all of these regulations play out, but it could be even, let's say, that a ship going up to Stockton or up to Sacramento, and I'm not even sure what the salinity levels are during certain times of the year in Venetia, where you don't have that alkalinity from in brackish water or fresh water to neutralize that acid going overboard. And they are going to be monitoring the plume of wastewater as it comes off the ship, and within a certain buffer zone or a certain distance from the vessel, if it changes the alkalinity more than a certain amount, then you will have to go to a closed loop system. So in the closed loop system, the exhaust gas enters the scrubber and is sprayed with salt water that has been mixed with caustic soda. And then it has a small bleed off that's extracted from the closed loop and treated with an alkali agent again before being discharged overboard. It also is going to have the particulates removed. So with a closed loop system, you will have very little of this effluent being discharged into the ocean. And you are going to have to deal with the sludge that's created during this process will have to be stored on board and discharged safely and responsibly in the port. So a closed loop system, let's jump back. An open loop system, you are scrubbing the SOx out of the exhaust gas. You will retain the particulate matter, but you would discharge the salt water, which does have a lower, the pH has been shifted to us with the acid, and that would be discharged overboard. In a closed loop system, there's very little that goes overboard, and the system is recirculated and the water is treated. And the products that are left behind have to be stored on the board the vessel and discharged ashore. In a hybrid, the hybrid can be either run as an open or closed loop depending on regulatory requirements. Now again, we'll see how the industry responds to this and whether or not they will go with an open loop, closed, or hybrid. I would assume any vessels that are or will be going into areas with fresh water, large amounts of fresh water, would put into a hybrid system. And those ships that want to be able to go back and forth would also use that. So we'll see. The open loop is going to be the cheapest as far as installation cost. The hybrid gives them the ability to operate in fresh water as well as salt water. So this is a illustration of a open loop scrubber system that's produced by the company Wärtsilä. Your exhaust gas is going to be coming down through the venturi, and it will enter the scrubber near the bottom of that illustration. And then as it moves up, there are trays, and in those trays is a media, and you're spraying salt water onto those trays, and then the exhaust gas has to go around and up and through all this media, and that gives a lot of surface area. That will cool the gas. It will remove the SOx. It will remove the particulates, and then it will be exited out the top of the scrubber and out your stack. Now, with this open loop system, you are seeing that you have a pump, and they're calling it a reaction or a scrubber water pump, that you will have a circulation of this water, and then you will also, it tends to be though a once through system, but they're going to try and recapture in that residence tank the particulates through this hydrocyclone, and then those particulates would be kept in the sludge tank. And you also see that you have a wash water pump. So again, this is a once through as far as the salt water, but it will this is an open loop scrubber system produced by the Wärtsilä company, and it is made to remove SOx and SOx and particulates from your exhaust emissions from the main engine. And you can use both the main engine and auxiliary engines in these types of scrubber systems. Your exhaust gas will be moving down, what they're showing here is the venturi, and will enter the scrubber unit at the bottom. That gas will move upwards within the scrubber, and it will go through trays, and in those trays you have a media such as rock, or like it looks like a ping pong ball, and that gives a lot of surface area for that exhaust gas to work its way around, so it is in contact as much as possible with the exhaust gas. You'll also see a line going into the venturi itself, And that spray is to cool the exhaust gas down before it enters the scrubber unit. And then there's sprays as it moves up through the scrubber unit to remove the SOx and particulates. The exhaust gas will come out the top of the scrubber unit and then will exit your stack. This can be used on both the main and auxiliary engines. You have a scrubbing water pump and you have a reaction water pump. So this water is circulated, but it has salt water, a fair amount of salt water coming in continuously, and a fair amount of salt water being discharged continuously. And that water is used to, again, pick up the SOx. The sulfuric acid formation is neutralized by the natural alkalinity of the seawater, though it does raise the pH of the seawater. It does change it, and then that is discharged directly overboard. You'll see this residence tank, and the reason for that residence tank is that in coordination with what they're calling a hydrocyclone, and this wash water pump, that circulates this wastewater, and you are removing the particulates and storing that in a sludge tank. So the particulates shouldn't be, the majority of the particulates shouldn't be discharged overboard. Mainly you're going to pick them up and store them. In a closed loop system, then what we're doing is the scrubber water is continually circulated, and it has an alkali agent that would neutralize the water. And the alkali is going to keep your pH in line, and then you are going to be removing this alkalinity and the particulates, any solid formations, out and put it into a sludge tank. You will have a small amount of water that is being continually brought into this system, and there will be a small amount discharged over the side. But again, this is designed for use in freshwater system, and it will minimize the amount of acid that is being discharged overboard. And then with a hybrid, it can be operated as either a open or a closed system. Another subject as far as lowering NOx, and this is one way of removing NOx that is currently being used. And you have a fuel emulsifier by itself can be beneficial by homogenizing the fuel oil to disperse any sludge. This has been used for quite a few years, as in you're putting the fuel through an ultrasonic, and any small amounts of water and sludge bond to the fuel molecules, and it is said to give you better combustion. But what we're doing now is this water and fuel emulsions, which reduce NOx emissions by introducing water into the combustion chamber. So you can mix as much as 50% water in, and then that water, when it enters the combustion chamber after being injected, will flash into a gas from the heat, and it will absorb heat as it flashes. That will lower the temperature in the combustion chamber. Water emulsions show a significant reduction in NOx emissions with a relatively limited penalty in terms of increased fuel consumption. And they can reduce NOx by as much as somewhere around 70%. So it is sizable. Long-term experience is available from power plant engines operating up to 50% water added to the fuel. So again, this has been used shoreside, and it is a proven technology. On the two-stroke engine, up to a 10% NOx reduction for an equal percentage of water addition is possible. So one of the advantages of this system is you can use it at pretty much any load. So this can be used to, say, lower your NOx emissions as you're coming in and out of port, and it can be easily shut down. One of its disadvantages, though, is it does increase the viscosity of the fuel and requires a higher temperatures for injection. So either ultrasonic or mechanical types of homogenizer can be used to obtain the same level of NOx reduction. When operating on distillate fuel, it may be necessary to add additives to stabilize the emulsion. In other words, the water wants to come out of the distillate fuel, and it might be necessary to put in an additive for it to maintain its suspension. The addition of water to the heavy fuel oil by homogenization increases fuel viscosity, and to maintain the fuel viscosity within normal range, the temperature may need to be raised up to 150 C, or even in some cases 170 C. This is quite hot, and that in itself is a little bit of a concern, but it has these types of temperatures are being successfully used aboard ships. But again, it is a concern, and you do have to watch some of the parameters. Like one of them is going to be you're at twice the flash point of most of the marine fuels. So there is quite a bit of vapor that's going to be given off by this system. All right, and this is the simulator fuel oil the simulator fuel oil system, and you'll see on this that this is provided, and you can experiment with the fuel oil and water emission system, and it is put in right before the circulatory loop. And in this case, I've used it with up to about, on the simulator, with about 30% water emulsion, and the NOx dropped down from 12.4 grams per kilowatt hour to 8.3 grams per kilowatt hour. So if on the simulator, let's say we're going into Valdez and we're maneuvering at low loads, you could use this to reduce your NOx emissions. With the SCR, we'll talk about some more later on, but with the SCR, once you start to slow down, typically the temperatures in the exhaust gas get too low, and your SCR cannot be used at low loads. This can. Direct water injection is effective in reducing NOx by adding mass and stealing heat from the combustion process when water is evaporating. Water injection takes place prior to fuel injection, resulting in a cooler combustion space. And we're talking about you have a separate injector that is, or it can be combined, but it is spraying water directly into the combustion space to cool the combustion air. Now, Wärtsilä medium-speed engines with direct water injection systems feature a combined injection valve and nozzle for injecting water and fuel oil into the combustion chamber. The nozzle has two separate needles that are controlled separately. The system can be transferred to either mode at any load without affecting engine operation. So this is their injector, and again, it is a combined. Can be used for injecting fuel and for injecting water. And this has been used successfully for quite a few years on their medium speed engines to lower NOx. Selective catalytic reduction system is best suited to high load conditions. Now, this reaction that takes place at fairly high temperatures. So if you slow the engine down, you're going to have to shut the SCR system off. And the SCR has the potential to remove more NOx than by any other method. Up to 95% reduction in NOx emissions is possible with an SCR. The exhaust gas is mixed with ammonia before passing through a layer of special catalyst whereby the NOx is reduced to nitrogen and water. The reaction temperature must be held between 300 and 400 degrees C. If the temperature is too low, condensation of ammonium sulfates will destroy the catalyst. In other words, you have this very, very expensive catalyst up in the stack in the exhaust system that you will destroy if you run it at too low of temperatures. So you're going to be running this up at high load, not at low loads. Too high at temperatures, and the NH3 will burn rather than react with the nitrogen oxides. So anyway, you're injecting ammonia into this system, and it has a catalyst where with your nitrogen oxides. The nitrogen oxide is typically what you have is it'll be NO2, NO3. The X basically signifies is it can be different, right? You can have it can be again NO2, NO3, and even NO4. So it reacts. The nitrogen is separated from the oxygen, and your output is H2O and pure nitrogen. And your ammonia would be that NH3. And ammonia many times is in the form of urea, and urea is a more dilute form of ammonia. So this is graphically showing you that and talking about that in this reaction, you're stripping away the nitrogen from the oxygen, and you're recombining it so that your output is pure nitrogen and water. And you're injecting a urea into this for your NH3. Or it can be pure ammonia too. Pure ammonia they tend not to use on commercial ships because it can be quite dangerous with pure ammonia solutions. You may see it, but you'll have to be very careful when you are handling that material. So to keep the temperature with expected limits, the SCR catalyst must be located between the exhaust gas receiver and the turbocharger. The turbocharger is going to pull out too much heat. Today's turbochargers pull out a lot of heat and would reduce that exhaust gas temperature below what is feasible for use on this SCR. So as soon as your exhaust gas comes off the exhaust gas receiver, it has to go into your SCR catalyst, and then the output of that catalytic is then fed into the inlet of the turbocharger. And you have a process computer which controls the amount of ammonia injected into the exhaust gas based on the amount of NOx in the SCR output. And you've got to be careful on that you're just putting in the right amount of ammonia, because otherwise if you inject too much, that ammonia, and it's called slip, that ammonia slip will be exhausted out into the environment. So it's controlled by a computer, and it's an exact amount to maintain the NOx at the desired regulatory settings. And depending on what regulatory agencies and the amount of NOx that they say that you can have, you can just inject more ammonia or less ammonia. And the SCR is feasible on two-stroke diesel engines with only a minor impact on their engine performance. So this is an illustration from Burmeister Wain, and you can see this vaporizer. So coming off the exhaust gas receiver, it goes into this vaporizer and mixer unit, and that way you're trying to mix that ammonia in with your exhaust gas so that it's prepared to go into the catalyst. And then you have your SCR reactor. It enters that, and that is again going to strip away the nitrogen and recombine, and then it goes into the inlet of your turbocharger, drives the turbocharger, and then goes up through your stack. You'll also notice that there is a bypass provided, so you can bypass the SCR when it's not required. And this is the page on the simulator that we will be using in lesson 6, where you will operate a selective catalytic reduction system. And it is very accurate and it works quite well. But one of the things, as you go into pour it, you'll have to shut this down, and then you'll have to go over to the emulsification system, because again, once the temperature drops down, this will stop from being active and will immediately go into a standby mode. To help with this problem of being able to do it as lower loads, Right now, what's in development, and this is developmental only right now, is a cylinder bypass valve. In order to achieve the highest possible fuel flexibility and to ensure that the exhaust produces exhaust gas at the correct temperature for the SCR system at low engine loads, the cylinder bypass valve increases the exhaust gas temperature by reducing the mass of air through the cylinders. The mass flow through the turbochargers is maintained and combustion is nearly unaffected. The biggest challenge is the reduction of cooling air through the cylinders, increasing cylinder temperatures, and this low load method is in the developmental stages. So to increase the temperatures of the exhaust going into the selective catalytic reduction reactor, what can happen is the cylinder and SCR bypass valve would open and allow some of the air from the scavenging air receiver to be added into the outgoing exhaust gas. That would reduce the amount of air going into the scavenging air entering the cylinder. And with that, since you decrease the mass flow rate, you're going to increase the output temperature, the exhaust gas temperatures out of this engine. And then that SCR bypass will be adjusted back and forth to maintain the exhaust gas appropriate for entering the SCR reactor. And that was under development, but the reason for this is to try to use it at lower operating speeds. Another one that's being under development is exhaust gas recirculation and scavenging air moisturizing, SAM, which reduces the production of NOx by reducing the localized maximum combustion temperatures in the combustion chamber by reducing the concentration of oxygen and adding an inert media which has a high specific heat capacity when we're talking about CO2 and water vapor, and this is primarily from your EGR. So NOx production only takes place at very high temperatures, and then it increases exponentially with temperature. So if we reduce the temperatures in the combustion chamber, we will reduce the amount of NOx. So exhaust gas recirculation is a method of modifying the engine inlet air to reduce NOx. It has successfully been used in the 1970s on small four-stroke diesel engines used in the automotive sector. Some of the exhaust gas is cooled and cleaned before recirculation back to the scavenging air side. Its effect on NOx formation is partly due to reduction of the oxygen concentration in the combustion zone and partly due to the content of water and carbon dioxide in the exhaust gas. The burning of high sulfur heavy fuel oil is a challenge due to the presence of sulfuric acid and high solids content, and wet scrubbing of the exhaust gas is required for operation with HFO, heavy fuel oil. So this is an illustration of this. So what you're doing is you're taking the exhaust gas and you're going to clean a portion of it, right? You're going to clean it and scrub it, and you can see where it's shown with a cooler and a scrubber. And then you have an exhaust gas recirculation blower, which increases the pressure of this and adds it back into the scavenging air receiver. So in other words, you're taking some exhaust gas that has been cleaned and cooled, putting it back into the scavenging air receiver, and then that will then go into the combustion chamber. And again, you're putting in this inert gas that will help to reduce NOx formation. So the exhaust gas recirculation high-speed blower, this is an example of that, and it improves the process by putting a turbine with high-speed blower. This high-speed exhaust gas recirculation blower is based on a radial turbo compressor wheel running at 2 to 3 times higher speeds than a conventional B wheel. So anyway, these are a specialized blower that has been developed for the inert gas system. You also have an exhaust gas recirculation water treatment system, and it's an important part of the operating the exhaust gas recirculation system due to the following parameters. Contaminated scrubber water needs to be cleaned of soot particles to avoid clogging up the system. The correct dosing of caustic controlling the salt concentration in the scrubber water, compliance with IMO regulations for wash water discharge, and minimal pumpable sludge production. The water generated during combustion, which is condensed in the exhaust gas recirculation cooler, needs to be discharged to the sea in a clean condition. Centrifugal separators are utilized for cleaning of scrubber water that is supplied to the EGR unit and prior to discharge overboard. Now, these separators look very, very closely like a oil separator or a fuel separator, and produced by many of the same companies. All water supplied to the exhaust gas recirculation scrubber is cleaned in order to ensure reliable operation and to prevent deposits and scaling. Scrubber water quality is controlled by discharging a percentage of the flow overboard and by the addition of fresh water to the system. The quality of the scrubber water is defined by its pH value, salt concentration, and percentage of entrained solids. Water treatment systems must be in compliance with IMO wash water criteria in all operational modes. In other words, there are criteria now for the discharge of this wastewater over the side. And this is what the system looks like. And again, they're showing two centrifugal separators to remove the sludge out of this process. This can also, by the way, is not that different in looks from the ones from a scrubber unit. In other words, the scrubber for removal of SOx that we talked about earlier. So, scavenging air moisturizing. This is Burmeister Wayne, their latest one that's in development. And you have a first stage. Seawater injects a surplus of seawater saturation and cooling of hot air from the turbocharger compressor. The saltwater stage will provide a near 100% humidification of the scavenger. So you're atomizing and blowing salt water into the intake of this engine, and that's going to cool that hot air, exhaust gas intake, scavenging air, and its heat of compression from your turbochargers. It's going to cool that down, and it's going to humidify it. Then that salt water is caught and drained away, and then you have a freshwater stage, two freshwater stages that are near temperature neutral to the scavenging air. In other words, after it's cooled down. So what you're doing is you're spraying salt water. You're trying to recover as much as possible that salt water and discharge it over that hasn't atomized, and discharge that overboard. And then you have two freshwater stages after that, and the freshwater stages only act as cleaning stages for removal of any salt which may pass with the air from the saltwater stage. Alright, so this is showing that. You have this saltwater spray unit, and then you'll have a mist catcher, which is very typical to what has been used for years for removal of water from the scavenging air. And then that salt water, any that's not atomized, is drained away. And then you have the two freshwater stages where you're trying to catch any salt that would pass through. And then that is also removed. And then it would go into the main engine, and it will be cooled. By cooling and humidifying that incoming scavenging air, you're going to reduce your emissions, and by lowering the temperatures during the combustion process. So this is showing here what your salt contents on each one of these tanks. And again, what you're trying to do is you're trying to remove and make sure that none of that salt is going to be able to get into the engine. So the sea salts, any of that mixing in, can mix with vanadium and some of the other that comes in with the fuel and can damage the engine. So you want to have that water entering. The interesting part about this, though, is the salt water, not only are you spraying it in, but it's atomizing, right? It's turning into vapor. So you actually have a little bit of freshwater production, and your freshwater tanks will actually will increase, and some of that is drained over the side. So what is being pulled through as humidity is pure water, right? You're not pulling salt water down. The salt water is evaporating and leaving a brine, and then that that water then goes through the two freshwater stages to make sure that you're not going to have any salt being entrained and being carried into the engine. All right, so that concludes this presentation. I hope it has been helpful to you. Thank you very much.